A simple LED bulb can cost just a few dollars, but with over 15 billion units produced each year, they have built an industry worth more than $100 billion, illuminating almost every corner of the planet. The journey begins with a semiconductor chip smaller than a grain of dust, passing through assembly stages measured in micrometers, soldering gold wires thinner than a human hair, color conversion, protective encapsulation, and large-scale light testing, before becoming a lighting source for the entire world. Today, we're taking you to the heart of this process, where nearly invisible chips transform into billions of light sources that illuminate the planet each day. For over a century, humanity accepted a costly compromise, burning enormous amounts of energy just to produce a little light. From Edison's incandescent bulbs glowing with intense heat to fluorescent lamps filled with toxic mercury, the world yearned for a cleaner, cooler, and far more durable light source. It was from this demand for change that LED technology was born. Yet in its early days, the LED simply wasn't powerful enough. For decades, it remained confined to a secondary role, appearing only as faint red indicator lights on control panels, while incandescent and fluorescent lighting continued to dominate. But this very limitation posed a defining challenge. If a blue LED could be created, everything would change. In 1994, Japanese engineer Shuji Nakamura discovered an appropriate semiconductor material, allowing blue LEDs to emit light reliably for the first time. This breakthrough made white light possible and marked the beginning of a new era in human lighting. Every LED lamp begins with a semiconductor chip, and to create this chip, factories must start with crystalline substrates, most commonly sapphire. But before a crystal can be processed, humans must enter an almost absolutely clean environment. The entire chip manufacturing zone operates as a massive clean room, where a single microscopic dust particle can be enough to ruin thousands of chips at once. Engineers and technicians must don complete protective equipment, one-piece clean room suits, hoods, masks, gloves, and anti-static shoes, before passing through high-pressure air showers designed to eliminate any remaining dust or contaminants. Once conditions meet strict specifications, sapphire substrates are loaded into epitaxial reaction chambers, operating at extremely high temperatures. Gases containing gallium and nitrogen are then introduced, flowing over the sapphire surface and bonding atom by atom, crystallizing into ultra-thin layers far beyond the limits of human vision. Through this process, specialized semiconductor layers are formed and stacked in precise order, creating a p-n junction structure. It is within this junction that, when an electric current flows, charged particles collide and release energy in the form of light. This is the moment when LED light is born, at the atomic scale. After epitaxial growth, the wafer appears smooth and mirror-like to the naked eye. But in reality, its surface already contains millions of semiconductor structures that are not yet capable of producing light. To transform these structures into functional LED chips, the wafer must undergo the photolithography process. Inside a controlled yellow light environment, the wafer surface is covered with a photosensitive material called photoresist. Ultraviolet light is then projected through a precision mask, drawing microscopic patterns on the wafer with accuracy of a few micrometers. Unwanted regions are removed, leaving behind a complex network of ultra-fine circuit features. Next, the wafer is transferred into a vacuum chamber where an extremely thin layer of metal is deposited to form the electrical contacts. At this stage, the entire wafer has effectively become a massive light circuit board containing tens of thousands of individual LED chips, all formed simultaneously and waiting to be separated in the next production step. When the entire microcircuit structure has been fully formed on the wafer surface, the light's journey enters a decisive stage. Chip separation. Beneath its mirror-smooth appearance, the wafer is actually a microscopic map containing tens of thousands of identical LED chips arranged in perfect geometric order. The factory employs a high-energy laser system with extremely precise beam focusing. Guided along pre-calculated cutting lines between each chip, the laser cleanly cuts the wafer into thousands of small squares, minimizing cracks and residual stresses that could otherwise damage the internal structures. Each individual LED chip, once separated, measures only a few tens of millimeters, smaller than a needle tip, but contains within it a complete light-emitting region, semiconductor layers, and a fully formed p-n junction. Immediately after cutting, the LED chips pass through an automated inspection system. Each chip is briefly powered on to verify that it emits the correct color and operates at the appropriate voltage. Defective chips are removed on the spot. Only those that meet all specifications are allowed to continue their journey to the next step. After the wafer has been cut into thousands of tiny LED chips, they all remain firmly attached to a thin carrier film. In this state, robotic systems cannot pick up individual chips with micrometer-level precision. For this reason, the film is fed into a crystal expansion machine. Uniform tension is applied in 4 directions, stretching the film outward. As the film expands, the chips gradually separate from each other, increasing the spacing between them according to pre-calculated dimensions. The result is a perfectly ordered chip grid, where each die is uniformly spaced and precisely aligned. Once the expansion process is complete, the film carrying the uniformly separated chips is transferred to an automated pick-and-place system, ready to enter the chip bonding stage. Each microscopic LED chip is fixed onto a metal conductive frame composed of 2 terminals, the positive anode and negative cathode. An automatic chip bonding machine dispenses a precisely controlled dot of thermally conductive adhesive onto a designated position on the conductive frame. This adhesive plays a dual role. It securely anchors the chip in place while providing an efficient path for heat dissipation. The expanded film carrying the separated chips is then fed into the machine. Industrial vision cameras scan the entire surface, automatically identifying the exact coordinates of each chip as well as the metal pads on the conductive frame. The robotic arm operates at near instantaneous speed. Pick up, rotate, align, and place, each cycle taking only fractions of milliseconds. Precision at this stage is critical. Misalignment of just 20 to 30 micrometers can cause color shift, reduce LED lifespan, or even lead to immediate failure. Once an entire strip of chips has been placed, the conductive frames are transferred into a thermal curing oven where stable temperature is maintained for several minutes, allowing the adhesive to fully harden. After the LED chip has been fully fixed onto the metal conductive frame, the LED tray is transferred into an automatic wire bonding machine. A spool of 99% pure gold wire with a diameter of 18 to 25 micrometers, 3 to 5 times thinner than a human hair, is fed into the system. High-resolution industrial cameras scan each individual chip and its corresponding conductive terminals, calculating their exact position with accuracy of a few micrometers. Using a combination of heat and ultrasonic energy, the machine forms a small gold ball at the wire's end. This ball is pressed onto the chip's electrode, creating the first bond point. Immediately after, the wire is drawn in a carefully formed arc and lowered onto the metal conductor to form the second bond. The wire is then cut and the machine moves to the next chip. Once gold wire bonding and initial inspection are completed, the LED frames are transferred to the phosphor coating area. Raw phosphor powder is first weighed using an analytical balance with 0.0001 gram precision. According to the target color temperature, engineers mix several phosphor powders, yellow, orange, pink, and other spectral modifiers, according to precisely calculated ratios. After weighing, the mixture is sent to a high-speed mixer where the phosphor powder is uniformly dispersed throughout the epoxy solution. Then, the phosphor epoxy mixture is loaded into the dispensing cylinder of a phosphor dotting machine. Thousands of LEDs mounted on LED frames are fed into the machine chamber, where ultra-fine dispensing needles deposit an extremely consistent volume of the mixture onto each individual LED chip. This thin coating is responsible for converting the chip's native blue light into the white or amber light visible to the human eye. Once coating is complete, the entire LED tray is placed in a curing oven operating at approximately 150 degrees Celsius. At this controlled temperature, the epoxy fully hardens, permanently locking the phosphor layer in place. The most fascinating detail is this: no semiconductor chip naturally emits white light. In reality, LED chips always produce blue light. It's the yellow phosphor layer that transforms this blue emission into the white light we perceive. This conversion process is the hidden secret behind modern LED color technology. Once the LED chips and gold wires are securely fixed in place, the entire conductive frame strip is transferred to the epoxy molding area, the stage where the LED's characteristic transparent lens is formed. Liquid epoxy resin is injected into steel molds containing hundreds of precisely formed cavities designed to create standard LED shapes such as 5mm round heads, flat tops, or oval lenses. The filled molds are then moved into a circulating thermal oven, operating at approximately 120 to 150 degrees Celsius. Under this carefully controlled heat, the epoxy undergoes molecular cross-linking, gradually transforming from a viscous liquid into a solid crystalline structure. When the curing process is complete, the LEDs are released from the mold in their final form. Once the epoxy has fully hardened, the steel mold is opened, revealing a long LED strip containing hundreds of individual lamps, looking almost finished but still all connected together on a single metal conductive frame. The LED strip is then fed into a degating machine. Inside, a system of precisely aligned cutting blades and metal punching mechanisms operate with extreme precision. In just seconds, the thin connecting bars linking the LEDs are cleanly cut, releasing each LED package as an individual unit. After being separated from the metal frame, each individual LED is fed into an automated electro-optical testing system. In a brief instant, the LED is powered on and lit, allowing industrial cameras and optical sensors to precisely measure brightness, color output, operating voltage, and color temperature. At this very stage, the sorting system begins its operation. Based on the collected measurement data, each LED is sorted into distinct groups according to brightness level, color characteristics, and electrical voltage. Pneumatic mechanisms quickly direct each LED into its corresponding compartment, ensuring that when these LEDs are assembled together on the same light strip or lighting panel, they emit uniform light without color shift or brightness inconsistency. LEDs that pass all inspections move to final packaging. They are carefully dried and sealed in moisture-resistant bags or trays labeled with sorting data, batch codes, and production dates. Finished shipments are then secured and transported worldwide to factories producing LED strips, displays, toys, and electronic devices, ready for final assembly and delivery to consumers. Today, LED lighting has become an indispensable part of modern life. From sapphire substrate to the white light we use every day, each LED is the result of hundreds of microscopic precision steps, where every micrometer, every degree of temperature, and every millisecond determines the final product quality. Now that you know what's behind a simple LED, a question arises. An LED costs a few cents to produce, but how many resources, energy, and expertise are sacrificed for it to be disposable? Progress or technological waste? We want to know your opinion in the comments. If you enjoyed this documentary, don't forget to like, subscribe, and activate the bell so you don't miss any of our content. But don't leave yet, that's not all. The continuation of this video will be just as fascinating, so stay with us until the end.
Every year, more than 215 million LED TVs are sold worldwide. To meet this enormous demand, large high-tech factories must operate tirelessly, day and night, with a perfectly orchestrated schedule. But how exactly is a modern smart TV manufactured? To find out, let's go inside the facilities of a world leader in LED TVs and follow step by step the creation of a complete device. The evolution of LED smart TVs is a story of successive innovations that have transformed home entertainment. From the old black and white sets of the mid-20th century, we moved in the 1960s to color television. And then, in the 1990s, to flat screens that slimmed down screens and freed up living room space. The major leap forward came in the 2000s with the rise of LED panels. Thanks to light-emitting diodes, televisions became thinner, more energy efficient, and capable of displaying vibrant colors and enhanced contrast. But the real revolution was making them smart. Connected to the internet, able to install apps, access platforms like Netflix and YouTube, and interact with our smartphones and voice assistants. Today, with 4K and 8K resolutions, ultra-thin designs, advanced electronics, and comprehensive connectivity, these televisions offer surgically precise images, accurate colors, and features that make them the nerve center of home entertainment. More than just screens, they are objects where engineering and design intertwine and have become indispensable in modern homes. So, what goes into the manufacturing of today's televisions? The first major chapter concerns the creation of the screen, one of the most crucial parts of the device. LED smart TV panels are based on a liquid crystal display, LCD. This is what modulates the light to form sharp images. To manufacture this panel, a process often described as a sandwich is used. In practice, two ultra-thin sheets of glass are joined together like two slices of bread. Between these sheets of glass, a layer of liquid crystals is deposited. Under the influence of tiny electric fields, these molecules orient themselves and allow more or less light to pass through. This is the principle that allows each pixel, the millions of tiny dots that make up the image, to open, close, or filter the light. But without control, this liquid crystal would be silent. Therefore, a matrix of transistors, TFTs, tiny switches that individually address each pixel, is added to one of the glass sheets. These transistors determine, down to the microsecond, the brightness and hue of each pixel in the image. On the other sheet of glass, colored filters are deposited: red, green, and blue, the three primary colors of light. By precisely adjusting these three components on each subpixel, millions of shades and gradients are recreated, giving images their richness and realism. Thus, when we contemplate a highly detailed scene, a sporting event, a dark film, a vibrant cartoon, it is the orchestration of these filters, the liquid crystals, and the transistors that allows each pixel to change color and intensity with striking precision. After the LCD panel comes the key step of lighting, the installation of the LEDs, light-emitting diodes that will illuminate the panel from behind, backlighting. These are what make the image visible and contribute to the perception of contrast. The LEDs are never placed randomly. They are aligned in strips and distributed according to the chosen architecture, edge backlighting, or full array behind the entire surface. To ensure millimeter-precise positioning, an automated robot places each strip in the correct position, secures the connectors, verifies the orientation, and checks the consistency of the spacing. This perfect geometry guarantees a homogeneous distribution of light and avoids areas that are too bright or too dark. However, even an LED grid isn't enough to make the light perfectly uniform. Therefore, a light guide plate LGP is added, often a plexiglass panel, along with diffusion films and sometimes prismatic films. The guide plate captures the light from the LEDs and distributes it across the entire surface. The films soften and blend the light, optimizing its uniformity and direction. Ultimately, each area of the screen receives the same light intensity, an essential condition for a smooth, bright, and consistent image. Thanks to this combination, televisions produce remarkable image quality with consistent colors and deeper blacks for a visually pleasing experience in every scene. The production line then moves on to the electronics. This is the television's nervous system. Several circuit boards, PCBs, are manufactured and tested. Two of them are central. The first component, the motherboard, is the brain of the device. It manages signal reception, antenna, cable, HDMI, video processing, scaling, noise reduction, motion enhancement, audio processing, and connectivity, Wi-Fi, Ethernet, Bluetooth, for accessing streaming services and updates. The second component, the power board, converts and distributes electrical power to the various sub-assemblies: LED backlighting, video processor, memory, speakers, and ports. It must be stable and secure, preventing overcurrents and protecting sensitive components. Assembling these boards is not simply a matter of pressing a button. Even though surface mount technology, SMT, is highly automated, part of the integration process remains manual and meticulous. Technicians and operators insert certain components, attach connectors, and add capacitors, resistors, and specific transistors. Then comes soldering, wave soldering, or reflow soldering, which ensures strong and conductive connections. Each joint must be clean, without cold solder, joints, or metal bridges. The slightest defect can lead to random malfunctions. Optical inspection and sometimes X-rays validate the quality of the solder joints. Once the electronics are ready, work begins on the casing, the external frame that protects the internal components and gives the television its final appearance. Injection molding presses mold the frames and rear panels from polymers. The heated and liquefied plastic is injected under high pressure into precision molds. then cooled to set the shape. This method ensures lightweight yet robust parts with tight tolerances, perfectly adapted to each screen diagonal. The components are then adjusted and screwed in place. The panel is placed in the chassis, the circuit boards are secured, the ribbon cables and wires are neatly routed, the speakers are installed, and the ports, our HDMI, USB network, are secured in their openings. The final assembly combines rigidity and aesthetics to create a solid, slim, and elegant product. At this stage, the television appears ready, but it must pass a battery of demanding tests. First, the image test. Test benches illuminate test patterns: red, green, blue, gradients, checkerboard, gray, while high-sensitivity scanners inspect the panel to detect any defective pixels or imperfect uniformity. Banding, clouding, and brightness uniformity are also checked. Next, the audio tests. The speakers play sequences of frequencies and real-world content: voice, music, effects, distortion, frequency response, stereo imaging, and audio output are measured for clear reproduction, free from crackling or dropouts. Finally, the electrical tests. Voltage stability, power consumption, short-circuit protection, startup and shutdown behavior, and resistance to repeated cycles. Each measurement must fall within strict ranges to guarantee reliability and safety. Once the hardware has passed all these stages, the system's software is installed, transforming the television into a true smart TV. This software, the operating system and core applications, controls the interface, Wi-Fi connection, networking, optional voice control, remote control pairing, and provides access to streaming platforms, picture profiles, cinema, games, sports, audio settings, clear voice, spatialization, quick inputs, and OTA updates are also configured. A series of final tests verifies the interface's fluidity, the stability of the apps, the connection quality, the responsiveness of the controls, and compatibility with peripherals, consoles, soundbars, HDMI dongles. The final stretch is packaging. It must protect the device during transport, sometimes over thousands of kilometers. We use a reinforced cardboard box sized to the screen's diagonal, with corner protectors and foam padding to absorb shocks and vibrations. The screen is often protected by a film, and anti-static bags cover sensitive areas. Inside the box, we add a user manual, the remote control and its batteries, the power cord, as well as the cables needed for installation, and the stand/screws or mounting kit if included. Once sealed, the televisions are palletized, shrink-wrapped, and then loaded onto trucks bound for distribution centers or directly to retailers. This process ensures that the device arrives at the customer's home in perfect condition, ready to be installed and enjoyed from the very first use. And that's how these industrial facilities produce, year after year, millions of smart TVs that find their way into our living rooms, become the heart of family entertainment, and connect to our entire digital ecosystem. Now it's your turn. What do you think of this fascinating manufacturing chain, from the photonics of LEDs to the algorithms that bring the image to life? If you enjoyed this documentary, then don't forget to like, subscribe, and turn on notifications so you don't miss any of our content.